In this section, we will be going further with deep deterministic policy gradients. We'll go over the DDPG algorithm, some extensions to DDPG, and show DDPG in PyTorch. We'll then conclude this course with a discussion on some of the interesting topics in the field of deep reinforcement learning. Here, we will first look into performing deep deterministic policy gradients. Let me give you a quick introduction. So, deep deterministic policy gradients combine aspects of deep Q networks, policy gradients, and actor-critic architecture that we've gone over in previous sections. DDPG has DQN-like off-policy updates for continuous action spaces while directly optimizing the policy with an actor-critic architecture. Now, before we go into the DDPG code, we'll explore an important concept behind DDPG, the deterministic policy gradient. The deterministic policy gradient is the expected gradient of the action value function. It is deterministic, that is, integrated over state space, and not stochastic, making it much more efficient to estimate. In the original DPG paper, the authors proved the DPG theorem, which shows that using the DPG is valid as the stochastic policy gradient converges to the DPG. The theorem allows us to use the efficiency of the deterministic policy gradient. We'll see deterministic policy gradient usage in DDPG in the next slide. DDPG is the deep RL implementation of DPG. It has an actor-critic architecture with elements of DQN-like off-policy learning, experience replay, and target network updating. Also, unlike DQN, DDPG works in continuous action spaces. In DQN, we use Q-learning to get the target update, whereas in DDPG, we use deterministic policy gradients to get the target. Deterministic policy gradients allow DDPG to find and use a target policy for its TD updates. The DPG formula in the lower left shows the updates for the actor network. Let's have a closer look here. The second term is the gradient of the actor output mu, as we saw in prior PG methods. This is multiplied by the output of the gradient of the critic network Q. Well, the theory behind DPG is a bit hard to grasp at first, but I'm sure, after seeing the DDPG network in the upcoming code, you have a better understanding of the concepts discussed. Let's have a look at the code example that uses the DDPG network in PyTorch with a continuous lunar lander environment. Let's look at some code. In this video, we're going to focus on the DDPG architecture, in particular the actor-critic network setup. Next video, we'll go over the entire DDPG algorithm. So let's build upon the actor-critic network that we used last section. So here we have the actor network, and we need to make a couple alterations for the actor network for DDPG. One thing is the inclusion of the action max. We enter an action max parameter, and then for the output, before we used a linear layer for the output. Here we're going to use the tanh function. That torch.tanh will squash the output function between -1 and 1. That way the action values will be between -1 and 1. However, some environments don't require an action value between -1 and 1. They want it between a different range. For example, if they want the action values between the range -2 and 2, you need to make an adjustment. That's where the action max value comes in. We'll take that squashed output, that's squashed by the torch.tanh, and we'll multiply it by the self.actionMax value. All right, now on to the critic network. All right, for the critic network, we're not using the action max, and the output's just going to be a linear layer. The additional thing we're doing for the critic network that we didn't do before in the actor critic network is now here in the DDPG critic network, we are relying on the actions as another input. The critic is with respect to the actor's output of the actions. So for forward, we have X, which stands for the state input. We're going to add an A, and this A stands for the action input. And for the first layer, instead of just having X as the input, we're going to have a concatenation of X and A along the column. And to do that in PyTorch, we use the torch.cat call. And since we're concatenating along the columns, we're going to set the dimensions equal to 1. All right, so that's the actor critic DDPG version. Then down below, when we run the DDPG in the train function, will input not only the state values, but also the action values. So here's an example. So the critic network, we enter the batch of state values, batch of action values. Here's another example with the critic network. Note there's not only a state batch, but an action batch. That's because the critic networks, we find the values with respect to the output of the actor network's actions. All right, so that's it for the DDPG code for this video.